So good afternoon, everyone. It's really nice to be here and also see many people from the Siemens collaboration. And of course, it's always a pleasure to be back in Cargese. So today I will start discussing many-body localization in the sense that Thierry already mentioned it. So I will focus more on dynamics far away from the ground states in many-body systems, such that you don't have to worry about all the rich physics that occurs at low temperatures and will go to high or even infinite temperature. And we would be interested in questions like thermalization or lack thereof due to localization. And we will often find it useful to take more quantum information perspective and use things like entanglement, which I will also motivate and explain. So yeah, and I can only join Carlo and Thierry in saying that if something isn't clear, anything isn't clear, please stop me and ask, because my goal is not to get through the end of the slides, but to sort of give you an idea of what the field looks like and what are the main ideas and main things we've understood, and there are a lot of things we have not understood. And since I had to wake up at 5 a.m., probably the number of things that would be unclear would be pretty high. So don't hesitate. So we'll be talking about dynamics of interacting systems, right? And there is this very basic fact that to describe a many-body wave function, so for example of n spins 1/2, you really need a lot of parameters. You would need 2 to the power n amplitudes to fully specify a wave function, right? And that's at the computational level. That's why these problems are so hard. And in a way, that's the inspiration. This hardness is the inspiration to the very idea of the quantum simulator, right? So we need to make programmable machines which would function differently from classical computers and which would allow us to tackle this quantum exponential wall. And of course, you will hear a lot more about it in the lecture of Emmanuel tomorrow. So, but just to introduce the basic things a little bit. So now we have such quantum simulators, and ultra-cold atoms are the prime example of those. And the great thing about the systems is that they're extremely tunable, so you can change dimensionality, you can control the lattice potential, and also tune interactions between the atoms. And although you can use the systems to try to understand, for example, what strongly correlated materials do to, or at least some aspects of strongly correlated materials, the systems are also very much unlike conventional materials in that they're first of all largely isolated from the thermal reservoir, so there is no phonon or external heat bath. And moreover, compared to, for example, a metal, the systems are very dilute, right? And therefore, the intrinsic time scales for their dynamics are very long. And that allows experimentalists to study non-equilibrium dynamics of the systems and image it in real time with single-site resolution. So this really opens this window into highly non-equilibrium phenomena in isolated quantum systems. And I think more or less throughout all of this lecture, I'll assume that our system is isolated, so there is no dissipation, right? Of course, it is true only approximately. There is always some weak dissipation present, which introduces a time scale beyond which we have to worry about it. So let's ignore it for now. Now, types of experiments that the systems allow one to do are also quite different from the traditional solid-state experiments, right? So rather than measuring conductivity, which was maybe the #1 thing that comes to mind when you think about localization, Anderson localization and Anderson insulators. Here, for example, very typical experiment is a quantum quench. So you can prepare your system in some, say, relatively simple initial state in this case, where atoms are sitting in some pattern in a lattice. Then you let them interact and go, and then you can see how their interactions and kinetic energy make them move around, and you can image their wave function with single-site resolution in real time using quantum gas microscope. So here what you see is actually atoms in 2 dimensions spreading in the disordered potential, and you can see how they fill out. So they're prepared in half the lattice, and then you can see how they spread or not spread, which would signal localization. Another important class of non-equilibrium phenomena are cases where you're periodically driving the system, right? So by applying external fields, you modulate parameters periodically in time, and so we will hopefully get to that. There are quite a few platforms where different facets of non-equilibrium phenomena are studied, so ranging from cold atoms to trapped ions, also arrays of superconducting qubits, and Rydberg atom arrays. Right, so each system comes with its own set of capabilities where certain class of non-equilibrium phenomena are easier to access. So now, let's start with a basic, with a very basic question. Right, so we would like to understand, starting, for example, from the setup of a quantum quench. So say I have a generic interacting system of spins, for example. Let's assume that interactions are short range, such that there is degree of locality, and we are doing a quantum quench, and we would like to understand whether the system reaches a steady state, right? Does it equilibrate? To what state, and how is this equilibrium approached? So broadly, we would like to understand, what are the possibilities? How much universality is there? And ideally have some unified picture like what we have in thermal equilibrium, where symmetry breaking gives us a guiding principle to classify the possibilities. Right, but we are, as you will see, I think we are really at the very beginning of this quest. And so of course this is, it's clearly a very fundamental question, right? Because it's very basic and it goes to the heart of quantum statistical mechanics. But also people, start to start to explore it more and more, because this is closely intertwined with the desire to control the synthetic systems more efficiently, right? So, and there are many connections, for example, to quantum algorithms which are emerging, because whenever you want to control a system, you bring it out of equilibrium, right? And that brings you back to the same basic questions. So now our intuition tells us that normally when you push something far from equilibrium, things would gradually mix, and this non-uniformity would disappear, and your system would find state of thermal equilibrium, right? And let's see, right? And in classical systems, property that's underlying that is ergodicity. So your dynamical system is evolving, and it can explore all the corners of the phase space allowed by the global conservation laws, right? So you have global energy conservation, but otherwise you go anywhere in your phase space, and that's ergodicity. So that's simple cartoon in a stadium billiard. And from this, from this notion of ergodicity, ultimately, so that's the basic postulate of statistical mechanics, from which you derive all other notions like entropy, temperature, and so on. Now, Anderson pointed out, already, many years ago that quantum mechanical systems might not always be ergodic, right? And the basic mechanism is Anderson localization. So while he was interested in the problem of disordered interacting spins, right? Problem was too hard even for him, so he solved the single particle problem. But then in this famous paper, so he makes a comment that this would be a system in which an approach to equilibrium is impossible, right? So he clearly already back then appreciated that this would be something interesting, not only from the point of view of transport, right, but also from the point of view of statistical mechanics. Now, as Thierry already described, so that's a difficult problem, right? And it really took many brilliant people thinking about it over generations and making various various steps until more recently with the works of Dennis Aleni-Ralschuler and also Igor Gorny and Sasha Mirlin and Dima Polyakov, so where really the picture emerged that there can be localization in the interacting systems. So you can start with a single particle Anderson insulator, and then under certain conditions, if you add interactions and finite density of particles, localization can persist, right? And of course, non-interacting particles are something special, right? It's doesn't happen in, for example, in a material naturally, but many-body localization. So it is a generic non-ergodic phase which does not thermalize, right? And so more recently, this driven by this philosophy, let's say, coming more from the quantum simulation and thinking about quantum information side of this phenomena, right? More, there has been a lot of progress in both understanding the structure of the states and also exploring new opportunities that come from the fact that these systems avoid thermalization. And that's what I'll focus on. So I assume that maybe Dennis will tell you a bit more about sort of techniques which lead to this these foundational works, right? So I'll focus on the stuff that happened a little bit afterwards. And so once again, right, so here we want to put all the difficult things together. So you have interactions, disorder, and you want to push the system highly out of equilibrium. So naturally, things that can be done analytically are relatively limited, but nevertheless, I'll give you a flavor of what one can do and where the bottlenecks are. And so I've mentioned entanglement, so let me define it, and then we will use it later on. So let's consider our system of n spins, right? And let's say it is in some pure many-body state psi. And we can ask, so it's a big Hilbert space of dimension 2 to the power n, right? And in that big Hilbert space, there are states that we know and love, which are classical states, right? They're tiny submanifold here, tiny corner of this big Hilbert space. So we can ask, well, this state psi, how non-classical is it? And one way to quantify it is by looking at its entanglement. And the way you do it, so you look at a subsystem, right? So for example, I take this chunk of spins A, and then I compute a reduced density matrix of this chunk of spins, right? So I trace out everything else and just look at the subsystem. Then generally, even though my state of my big system is pure, this subsystem would appear to be in the mixed state. So it sees everything else as as environment, right? And then we can simply compute the von Neumann entropy of this reduced density matrix, right? The usual trace rho log rho, and that's the definition of the entanglement entropy, with respect to the state and the subsystem, right? So to get an idea of how non-classical a state is, what you do is you look at different subsystems, right? Smaller, bigger, and how entanglement entropy depends on the size of the subsystem and the type of cut you're making. And so simplest example, if you have two spins in a singlet state, right, then if you look at one of them, its density matrix would be completely mixed, right? And that would give you entanglement, that would give you entropy of log 2. Right? If you have analog of this state for k spins, then entanglement entropy would be k log 2. Now, why do we care so much about entanglement of many-body states? So one very basic reason is that it gives you some insight into the computational complexity of the state. So states which don't have a lot of entanglement, turns out that you can approximate them very efficiently with much fewer parameters. So naively, I need 2 to the power n parameters, but if I have a state that is such that the entanglement entropy for a subsystem scales proportional to the volume of its boundary, right? Which intuitively means that only things that are nearby are strongly entangled, right? There is somehow, short-range entanglement, you could say, in the system. Such states can be efficiently compressed using only a polynomial number of parameters in the system size, right? So it is quite a remarkable result, right? It tells you that there is a big subclass of states which are actually not so complicated. And these are called area law entangled or volume or boundary law entangled states. And most ground states of systems with local interactions are in this class, right? And there are many powerful numerical techniques. Generally, let's refer them as tensor networks methods which take advantage of that and allow you to simulate those states efficiently. Now, on the opposite end of the spectrum, you have states with a lot of entanglement, where entanglement of a subsystem generally scales proportional to its volume. And for such states, this does not work, right? You can, of course, think of other approximate ways of describing them in terms of energy density and, keeping a few observables which are relevant, right? But a priori, these states are computationally hard, and you expect non-equilibrium states starting from, doing a quench from some generic initial state to be in this corner. Yeah?
What does it depend on? I mean, do you have some continuum in energies, or it's really system by system, or energy by energy, or state by state, and how much universality do you understand?
You mean which part? So this is so far, I'm just saying, okay, so,
Between area law and volume law, do you have everything?
So I think the fact that ground states have little entanglement, that's very universal, right? I mean, you can have some very special model fine-tuned that.
Does it continuously grow from some sort of area law to volume law, or you have a sudden transition somehow?
Yes, that's a very good question. So as soon as you have a finite energy density, finite energy of quasi-particles, and your system is thermalizing, then it's volume law. It would be a volume law, but the prefactor depends on the energy density, right? Yeah, that's a good question. But we'll see that this very much, what happens at for excited states very much depends on the kind of dynamics. So MPL is not like that. So in the beginning, I mentioned this, of course, there is thermalization, right? And there is this idea of ergodicity we have in the classical systems. But now what about quantum systems? So how do we understand thermalization in quantum many-body systems? Well, so that looks a bit different because, defining phase space for quantum many-body systems is not, if I give you an interacting system of spins, it's not so clear how to define phase space. So, but instead there is a, you think about the eigenstates, what the eigenstates look like of a quantum ergodic Hamiltonian. And there is a set of ideas called eigenstate normalization hypothesis, which tell you what are they like. And the intuition is actually very simple. So you have, if you look at eigenstate n, which is sufficiently highly excited, meaning finite energy density, then state of a subsystem looks as if your system was in a thermal equilibrium. So the reduced density matrix would be very close to a thermal density matrix computed, using microcanonical ensemble, for example, or Gibbs. Colloquially, you say that the system can act as a heat bath for its subsystems, right? So, and the origin of that is essentially because you so I don't know if you guys already encountered this language of resonances, but essentially when you couple two systems, there are a lot of resonances, and then your eigenstate is delocalized over possible configuration, possible product states of two subsystems. So I know this might sound mysterious, but if you would like to discuss this more, let me know. We can maybe towards the end do that. Now, from the point of view of entanglement, one immediate consequence of this hypothesis is that excited eigenstates would satisfy volume law entanglement, right? Because you would, reduced density matrix looks thermal. I have to look at its von Neumann entropy, so it would be just like thermodynamic entropy. And that scales proportional to the volume. So I don't think there is one definition, but let me say that this is a Hamiltonian for which, for any physical initial state, system would reach thermal equilibrium at sufficiently long times. And physical initial state I would call something that you can prepare in the lab in a time that's polynomial in the system size. So so scars, indeed, that's a good question about scars. So I think there you can also play with this definition a little bit, right? You can have systems where for all initial state except for some small number like scars, you would do that, you would thermalize, right? Yeah, you have some space, but let's say for an overwhelming majority of initial states, you would thermalize. Yes, exactly. Does it answer the question? So okay, so what happened? Here it is. Yeah. Now, of course, this might again sound a little bit mysterious, right? I'm saying, okay, this looks thermal in an eigenstate, but we know that preparing an eigenstate over many-body systems is very complicated, right? Because level spacing gets so small, you have 2 to the power n levels, right? So it would take you enormously long time to prepare an eigenstate, right? That's not what you do. So let's look at this a little bit closer, and let's ask what are matrix elements of physical observables like for a quantum ergodic system. And there, there are a lot of ideas which come from the random matrix theory. And random matrix, I mean, of course, it's a very useful, theory in many contexts. So here, in this context, it more or less gives you a toy model of a thermalizing system, if you wish. And so just a small reminder. So for example, I can consider an ensemble of n by n matrices where each entry, right, which are Hermitian, and each entry is just random, right? And they're distributed according to the same Gaussian distribution. so this is an ensemble that's invariant under unitary transformations, right? And there is a couple of things which are important for us. So first of all, you can expect that this is a system where so this Hamiltonian, let's say it's acting on some basis of states, right? And it couples every state in that basis to every other state. So you expect the eigenfunctions to be fully delocalized over this space, right? And that's what happens. So eigenstates look like random vectors in that space. One consequence of that is that they really do not like being close in energy. There is some typical level spacing, right? But then it is probability of finding two nearby levels much closer than the average level spacing is strongly suppressed. And that's exactly because they're delocalized, so they can talk to each other very efficiently because of that, right? And that leads to so-called Wigner-Dyson level statistics that tells you that probability of finding two levels with very close energy vanishes as some power of the difference, and that's what is referred to as a level repulsion, and that's a signature of taken as a signature of ergodicity and quantum chaos. Use of this has long history, starting I guess probably in the 80s when people were studying billiards, right? Billiards and things like that. But we are going to see how this plays out in the many-body context. Now, what about the structure of the eigenstates? Yeah.
Sorry, I don't understand why the eigenstates are delocalized, because the Hamiltonian is random, right?
Mm-hmm.
So I would expect it to be localized in space.
Mm-hmm. Yes, so this is right. So this is let's consider just two levels, right? And right, so I have some diagonal energies, and then I have off-diagonal matrix element, right? So typically, what you have to look at is essentially ratio of V12 over the energy difference, right? If this is small, then indeed your eigenstates are close to being fully on site 1 or site 2, right? So that's localization. If they are, if this is of order 1, then you expect them to hybridize strongly, because you cannot do perturbation theory, right? Or think about the opposite limit when E1 minus E2 is much smaller than the matrix element, then you have to do degenerate perturbation theory, right? So that's more or less what happens with the random matrices, because you have a big random matrix, you're coupled, right? You have a bunch of levels, right? But they're also coupled to a lot of other levels with a large matrix element. So you expect this to, resonances to be everywhere, and then just end up with a random wave function. Okay, so then if we accept this, that eigenstates are these random vectors in the Hilbert space, they're delocalized, and then you can also quickly, and intuitively understand what the matrix elements of some physical observable specified by operator all look like. Well, so I mean, the whole thing is kind of featureless, right? So you would have, if you're looking at the matrix element at the diagonal matrix element, you're sampling the full, your full Hilbert space. So it would be more or less given just by the average value of O. So it would be essentially a trace of O which would enter the diagonal matrix element. And the off-diagonal matrix element would be essentially given by the scalar product of two random vectors in the Hilbert space, right? Because N and M were some random vectors in this big Hilbert space. You acted, with O on state M, so it's still sort of a random vector, but no longer orthogonal to the n, right? But the scalar product of two random vectors is given by 1 over square root of the Hilbert space dimension, which is 1 over square root of n. And that's what I wrote in this formula, right? So of course, there is a factor coming, from the operator you take. It might have some overall scale, but that's not so important. So it goes as 1 over square root of the Hilbert space dimension times some random number, because of course sign can be random, right? There is a Gaussian distribution. So, and this is what matrix elements of operators in random matrix theory roughly look like. Now, why is this useful for us? So this gives you an insight into the structure of many-body eigenstates of thermalizing systems, which actually now have notion of locality. Because one big thing that random matrix is missing is that there is no locality, which of course we have typically in physical models. So now let's consider a system in d dimensions, right? D is greater than 0. So my Hamiltonian is sum of some local terms, like a spin chain, for example. And then so there is an ansatz due to Marx-Srednitsky, which extends this idea from random matrix theory to real systems with locality. And so so let me walk you through this ansatz. So what it tells is that if you look at the matrix element of a physical operator, diagonal part has this O of E bar, and E bar is the mean between the energies of the two states. So in this case, it would just become the energy of the state, right? If n is equal to m. And then you have for the off-diagonal matrix elements, you have this function f(O), which depends on the mean and on the difference of the two energies. There is also this random number that we saw on the previous slide. And then there is entropic factor, which plays the role of 1 over square root of the Hilbert space dimension. So if we have a system of n spins and we are living, in the middle of the spectrum at infinite temperature, right? This would go as 1 over square root of 2 to the power n. Make sense? No? Okay, let's pause and maybe ask. Because I see various degree of confusion, so I'll wait until it converts into a question. Because so, for example, if we buy that, so. Yes. No. So now, okay, so I have to be more clear here. So let's say AHR, so let's say we're dealing with a system of spins, right? And HR is something like SR, alpha, rather sigma R alpha, sigma beta R plus 1, with some, couplings J alpha beta. And these are Pauli matrices. So now I'm dealing with the Hilbert space of n spins, right? Or L, let's call them L spins 1/2. So M capital or N capital? Well, so right. So here n would be 2 to the power L. Yes, it is the full many-body. Yes, right. Mm-hmm. And so, of course, there is a lot more structure in a system with locality than we have in a random matrix. And that's what's encoded by this function O of and F, right, which are actually system specific, and they tell you two things. So, but first let me tell you, why this ansatz is useful. So okay, so first a little bit more about what's in it. So there is this function O that depends on energy, which gives you a diagonal matrix element. And the fact that your eigenstates look thermal just means that this would be the same as the microcanonical value of O at the corresponding energy, right? So that's putting in writing what I said a couple of slides ago. There is a new player here, which is this function F, which is a smooth function of E bar and omega, and this would be the function that is related ultimately to the spectral function of the operator O. So it would give you access to the dynamics. For example, if you do a quench, you start from a non-thermal value, how quickly you would settle in, right? That would be related to the Fourier transform of this function F. I'm also, again, I think eigenstate thermalization hypothesis is an active area of research in our community, but also in the high energy community, who are thinking about black holes and ADS-CFT correspondence. So I'm really being extremely superficial here, just to give you a basic idea. And now, so you can see that if you consider quantum quench and you prepare your system in some initial state, right, which is non-equilibrium, that state is a superposition of the eigenstates, right? And there would be, once you do that, the evolution is simply picking up phases, right? States with different energies would pick up different phases, but this part would always stay there because it's diagonal, it's time independent. And so roughly, what you can show is that system will thermalize starting from an arbitrary physical initial state, and the approach to equilibrium would be specified by the Fourier transform of this guy F, right? Why? Because off-diagonal matrix elements are the ones which would pick up phases, and then you would also have to average over. Essentially, you'll have to expand your initial state in terms of eigenstates, and look at those phases. So I'm not going to do this calculation here, but this, you can trust me that this can be done, and that was the point of how Srednitsky introduced this ansatz. So any questions? Because if it seems, if you guys buy it, we can move on. If not, I'm happy to try to give you some more intuition, because I find that this is one of those things, when you look at it, you wonder where it came from, but then if you spend enough time thinking about it, you convince yourself this is completely obvious. And more or less, I think the intuition, okay, let me give you another small piece of intuition that I find useful. So let me consider my system, for example, of spins, right? Let me cut it into left part and right part, and let me disconnect them, right? So my Hamiltonian would be part acting just on the spins on the left, part acting on spins on the right, and then the part that couples them across the boundary, right? So let me disconnect them. And then so HL would have eigenstates alpha, and HR would have eigenstates beta, right? While they're decoupled, the eigenstate of the whole system are alpha times beta with energy E alpha plus E beta. Next, I'm going to couple them, right? And coupling would introduce matrix elements between let's say alpha and beta, and then alpha prime and beta prime. And the whole question is how, what would true eigenstates of the coupled system look like in this original product state basis? And what, so in essence, you would have lots of resonances, and your true eigenstate I would look sort of like that, where E alpha plus E beta minus energy of state I, let's say, states of order of the norm of V or something like that. Right, so, and this would be Gaussian random numbers, sort of like in a random matrix theory. And why does it make sense? Well, you can sort of see self-consistency of this picture, right? So let's assume that ETH holds up to some scale, right? Then the key is that matrix element between two different eigenstates scales as V alpha alpha prime scales as 1 over square root of the Hilbert space dimension, which, so let me call it D. But I should compare it, just like we did in our 2x2 example, I should compare this matrix element to the level spacing. But level spacing goes as 1 over D, right? So you see that parametrically, so these are exponentially large numbers, so this would be much, much, much larger than the level spacing, so you're in the regime where there are lots of resonances. And it makes sense that this starts looking like a random matrix. Yes, yes. Now, thing is that there are probably easier things you can do to extract thermal properties than to extract an eigenstate, right? Because extracting an eigenstate, I mean, pretty much, you are limited to various versions of exact generalization to find an eigenstate.
This eigenstate of the big system which contains information, which must have a big entropy.
It will, so if your system is thermalizing, yes, it will have large entanglement entropy. Yeah. So any other questions? Okay. If not, so let me now move away from thermalization. And clearly thermalization is something, if you want to find new things in a quantum world, in this context of dynamics, you probably want to move away from it, because thermalization always leads to the same, featureless state where system just knows about the global conservation law and nothing more. So if you had, for example, some information you've written in your state, maybe you put these spins up, right? Or you made some spins entangled. As your system would be thermalizing, this information would become spread over more and more degrees of freedom, right? And your system would generate a lot of entanglement, and eventually everything you had written into the state would be lost and become unrecoverable, because it would require measuring an observable, which is really, really enormous, right? And what we do is local observables in the lab. And so from this, it seems like a good route to searching for new phenomena is actually first understanding how we could avoid or at least slow down thermalization. And so, many-body localization has been really the prime example of a system that does not thermalize, although there has been many other interesting ideas how to either avoid thermalization with quantum scars or slow it down, for example, with pre-thermalization and so on. So, but let's start with MBL and the ingredients. So ingredients that you need to get MBL are there are these three ingredients. So you have strong disorder, you have short-range interactions, and you consider the system strongly out of equilibrium in the sense that also TD specified that you consider states which have finite energy density or finite density of quasi-particles. So here is a small illustration of that. So if I, for example, look at a spin chain, which is, so here I have, these two terms are XXZ spin chain with random on-site field drawn from some distribution, with variance W. So this system would have a spectrum, right? Spectrum is bounded. It would go from some minimal value to the maximum. Both of them would be in general proportional to the system size, L. And then so we want to be looking at the system at some energy E, right? Such that distance from E to the extremal values of the energy divided by L stays constant as we take the system size to infinity, right? That means being far from either the ground state or the anti-ground state, but of course, anti-ground state is the same as ground state. Like I just changed the sign of the Hamiltonian, right? So that's where we want to be at. Now, density of states in this situation, so it's it is very strongly peaked in the middle of the band. It becomes exponentially large, and being at infinite temperature means that you want to be really right in the middle where the density of states is the highest and is of the order of 2 to the power L. And in brief, so many-body localization arises generically in such models when you make disorder strong enough. So let's say we fix other parameters. So in this case, J and V I'm going to fix, and then I'm going to crank up disorder, and there would be a critical value above which we enter many-body localized phase. And so let me tell you phenomenologically what this phase is like, and then we would spend a little bit of time discussing what is the status of this statement, what does it mean to be MBL, what we know for sure, what we don't know, and so on. And that I hope also will set the stage a little bit for several other talks on MBL that will follow. But let me start basic, right? So let's take this model, which has been historically the model that people looked at from the relatively early, numerical attempts, in particular by David Hughes and Vadim Oganisyan, and then Arijit Pal and Hughes, to probe MBL in a lattice model. So let's take this system. So here, this is a system we can fermionize, and then the Z term would play the role of interactions. First term is just on-site disorder, and then one signature that is very convenient to look at is exactly the level statistics. And that's what they did. So here is the level statistics as a function of disorder strength. And this parameter, so if you're wondering, so this is a parameter, this is not exactly the level spacing, but this is some proxy for level statistics. So this value being here tells you your system obeys, Wigner-Dyson random matrix statistics, which I guess after our discussion about ETH should not come as a surprise, right? Because the thing is really at smallest energy, it is really like a random matrix in many ways. While at strong disorder, system is going towards the Poisson value. Different curves are for different system sizes, right? And you see that seemingly this is becoming sharper. There is some, maybe some point where all of them sort of cross emerging, and that would naively you would identify with a transition from between the two phases. Mm-hmm. Which one? The IJ is nearest neighbor, yeah. Mm-hmm. Does it make sense? Yeah. Mm-hmm. So, and typically Poisson statistics taking as a signature of broken ergodicity. So that's what you see if you have an integrable system. And MBL you expect to be very non-ergodic, right? Because things are localized, so they cannot explore the full phase space. Another thing that they observed in this, in this numerical simulation was that a strong disorder, ETH breaks down. So here is difference between expectation value of some local observable, for example, sigma z on a given site, between two nearby eigenstates, many-body eigenstates. From ETH, you expect that, if you recall our ansatz, you expect that this would decay exponentially, right, with the system size. And that's what you see at weak disorder, so ETH holds here. But as you crank up disorder, it just flattens out. So there is a finite difference between nearby local observables. So that tells you that ETH is very strongly violated. Right, so that's another signature of MBL phase, is that ETH no longer works, which is of course logical. This is a phase that does not thermalize. Disorder here is an H, yeah. But you can, phenomenology does not change much if you make both of them disordered. Okay, so these were early works, which realized that you can study MBL at infinite temperature in the spin chains numerically, which has been extremely insightful. And so, in one insight, that came shortly afterwards, was related to entanglement. And this came, from asking a very natural question. So, are interactions actually important? Because you can say, well, from the point of view of conductivity, both have zero conductivity. Anderson insulator and the many-body localized insulator. So how do we make a distinction, right? And what the group of Joel Moore did, so they studied the quantum quench, same model as we had on the previous slide, starting from a product initial state, and then they asked, well, but how does entanglement spread? How does information propagate in the system? And they found something very interesting. So they found that, because naively you would say, well, system is localized, nothing should propagate, right? There is no transport of spin polarization, no transport of energy, right? But turns out there is something that is propagating. So here is what it looks like. So this is entanglement entropy between left and right subsystem, starting from 0 for a product state. When you have no interaction, it goes a little bit up and then flattens out, right, and stays constant. So, and that's just because there is one or two particles which are localized near the boundary, so they can hop back and forth, leading to some constant entanglement. But as soon as you turn on interactions, then you start seeing this very slow logarithmic growth of entanglement, logarithmic in time, right, which goes on for many decades. And so in this sort of gave an insight into underlying structure of the states and how we understand many of their properties now. And this is related to a very natural idea that, well, the system is non-ergodic. Things that are non-ergodic are usually, in some way integrable, and so is this one, right? So this system has a lot of quasi-local conservation laws. And so let me, again, give you a bit of flavor of how those work, and then we'll discuss, how one finds them and so on. And that maybe, that brings us a little bit to trying to develop some more, intuitive but also analytical understanding. What should we do if we try to develop a theory of these things? Well, so one limit in which you would like to work is strong disorder limit. So because if you start from an infinite disorder, so in our spin chain, I would just drop XX term, right, such that everything only depends on sigma z, and the system is trivial, right, trivially integrable. So you have sigma z on every side commutes with the Hamiltonian, and the eigenstates are simply product states, right? Each spin points up or down. But now, so let me add flip-flop terms, XX terms, while still staying in the in the MBL phase. And then so what, intuitively you can expect that, well, things would only change locally, such that I can make a sort of local transformation, right, or quasi-local transformation, entangle nearby spins a little bit, right, and then produce true set of eigenstates from the product states. That the product states are connected locally to the true eigenstates. So that's the basic, the basic picture and intuition about MBL phase. Once you do that, it's easy to imagine that the same unitary transformation which connects eigenstates to the product states would connect integral of motion, trivial integral of motion sigma z to non-trivial integral of motion tau z. They would be just, transformed sigma z's dressed by this quasi-local unitary. Right, so it's a little bit like finding action angle variables. So they're quasi-local in this case, meaning that if I look at the tau z operator, it would act in the vicinity of site I, and then it would only affect things far away exponentially weakly. Right, sort of like a localized Anderson wave function, right? But now this is an operator. This is a true operator in the many-body space. So said differently, MBL system has these qubits with infinite T1 time. So by themselves, they can never decay, but they can dephase. And just to resolve this little puzzle that we had, so we'll use that fact that they can still dephase due to residual interaction between them. But now one immediate, well, actually two immediate consequences of this picture are that first of all, MBL eigenstates are only area law entangled, right? If you create this entanglement locally, right, its transformation is quasi-local, all the eigenstate would be area law entangled. So they would all be like ground states of gapped systems. Well, almost all. Of course, there are rare resonances and things like that, but overwhelming majority would be area law entangled. And also you expect that ETH would be strongly violated because states which are nearby in energy would have typically different values of these tau z operators, right? And because tau z operators are quasi-local, they have overlaps and they have bearing on the physical observables. And because of that, if you measure, sigma z on a given site, sigma z has some overlap with tau z, it would jump, between different values between eigenstates which are really close in energy. And that explains to us why we saw this here, right? Why is it that you increase the system size, but the difference of expectation value of an observable between two nearby eigenstates stays sort of flat? So any questions?
In order to have MBL, is this sufficient or necessary to have these integrals somewhere present, even hidden?
I think so. It is definitely sufficient. Often I think this is taken as a definition of MBL, but I think this is a strong version of MBL. You can imagine, for example, you can imagine that if you have many-body mobility edge, which there are people who say there isn't a many-body mobility edge, although numerics says otherwise, and I think maybe Fabienne will show some. There, I think it's not so clear how to define this for part of the spectrum, right? So I think this is one example I can say where this is probably not necessary, right? But it is for sure sufficient. And if you're talking about systems which are fully localized, then I think this is probably a reasonable definition of MBL.
Does this mean that you're isolating isolated a part of phase space, or it's weakly isolated? Is it a
What
full
is
isolation, or
what is weakly isolated?
that means that it's not exactly conserved? But you know, if you have something that's exactly conserved, you have full isolation of your the part of your phase space. But here,
Yes, yes. So I think so. In generic situation, I think it's an open question, right? For one dimension, it's sufficiently strong disorder. If you allow yourself to have those exponential tails, then it can be an exact. You can construct an exact integral of motion. If you, of course, if you cut the tails, then you have something that commutes with the Hamiltonian up to an exponentially small
so you mean
correction.
the limit of the infinite system size, you have exact isolation.
Yes,
You have
yes,
enough,
yes, right. Which also translates into having, for example, your system not thermalizing at infinite times, right? That some, yeah, exactly. Right. So any other questions? No? Okay. So then let me move on. So as a side remark, okay, so before we get into the status of that, you know, how do we know that? Because of course this, you know, this is an appealing picture. First of all, there is a lot of numerics which supports it. For example, checking that eigenstates are areally entangled and constructing various versions of the integrals of motion. There is also a paper which presents rigorous proof in one dimension, and I'll say a couple of words about it, since I guess there are some mathematicians in the, at least I see one, in the but I'm sure there is more. So, but first of all, you know, a very simple implication of this picture is this dephasing and the slow propagation of information. So once you found the set of tau z operators which commute with the Hamiltonian, then you can say, well, my Hamiltonian, which again, you know, I get it in this form after doing the quasi-local unitary that diagonalizes the Hamiltonian, it would look like that in terms of tau operators. It would just involve tau z and then the products of tau z's, right? Because if there is tau x, then right away, you know, tau z does not commute with it. And so this, and intuitively, because everything happened quasi-locally, these residual interactions, they would come, you know, they would be exponentially suppressed between the two conserved operators in distance. So this is a little bit like Anderson localized wave functions, right? So also maybe to get intuition about this interaction, so think about Anderson insulator with weak interactions, and in the Hartree Fock, you would get exactly this type of interaction between two localized state, right, of the same form, which would decay exponentially with separation, and this would be single particle localization length. In interacting system, this is more complicated because you also have to worry about interaction not delocalizing you, which is a much harder problem, but the origin, hopefully, you know, you can get from a simple Hartree Fock type picture. And then so you have two of these pseudospins tau, they're interacting weakly, but then after the time, which is inverse in their interaction, which is exponentially large in the separation, they would develop phases of order pi, right? And if both of them were, you know, if they were pointing somewhere on the Bloch sphere, then they would dephase. And that's what underlies this logarithmic spreading of entanglement that we observed a couple of slides ago. And that's, of course, that's in contrast to ergodic systems where usually entanglement spreads linearly in time, right? Because, for example, you can have quasi-particles which just fly around and create entanglement, or Anderson insulator where there is no entanglement. There is saturation after a finite time. Another curious implication of this is that if you do a quantum quench, many-body localized system actually equilibrates, but to a state that's highly non-thermal, which remembers the average values of these tau z operators, right? So, but this equilibration is also consequence of interactions, because if you have an Anderson insulator, it would just keep oscillating. But here, due to dephasing, you scramble phases, but you maintain the probabilities of, you know, having given values of tau z's. So okay, I hope. So let me move on. So let me just say 2 words about matrix elements, because for the ergodic case we discussed Srednitsky ansatz, right? Matrix elements looked nice and smooth, and there was just a little bit of randomness due to that number Rmn. So here, of course, in the localized systems, matrix elements look completely different. So you expect matrix elements to generally be very, very small, right? To decay exponentially with the system size and some characteristic exponent kappa. Importantly, so this should be, typical matrix elements should be much smaller than the level spacing, right? Again, going back to the argument we had here. Because you can say, well, localized system, it should be something that if I add a perturbation here, nothing changes there, right? But that means that if I add a perturbation, then, and look how this makes me hop in the space of eigenstates in the same vein as we did here, right? So we started from some basis, and then we see how perturbation makes you hop and mix, either at least two resonances or not. So here I'm gonna apply local perturbation, and then I'm gonna see how that changes the eigenstate. So I'm gonna first go to the basis of eigenstates of Hamiltonian H, right? And the matrix elements of V would determine how I hope whether there are resonances or not. And for MBL phase, you expect that this matrix element typically would be much smaller than the level spacing, such that you have no resonances, right? You don't change things strongly. And moreover, in any localized system, things are broadly distributed, right? You generally expect log normal distributions. One nice way to account, because what matters is ratio of the matrix element to level spacing. So let us consider this ratio and log of it, and that there are reasons to call this a proxy many-body extension of the Thouless parameter, which I think most of you must have encountered, right? But this is a parameter which tells you if it is very large, you are very delocalized. If it's very small, you are localized, and then there is a flow associated with that. Well, I guess yeah. This is in the single particle context. This is related to conductance. So here, you see behavior kind of as you expect. So you see that in the thermal regime, this ratio grows as you increase the system size, because as expected from ETH. While on the MBL side, you see that it gets much smaller. So probability of finding resonances gets smaller, and this distribution becomes broader and broader, as you expect. So that's for the matrix elements, right? So matrix elements look extremely different also. Off-diagonal matrix elements look extremely different in the MBL phase. Now, okay, so I think we have a bit less than 20 minutes left, so maybe we can decide what we do in those 15 minutes. So one route would be to talk a little bit about the rigorous result of IMBRI, if you would like to see more, or if you would like to focus more on the intuition, then we can skip it and go forward. So, IMBRI. Okay. Okay, so this is an example. Route 2. Okay, well, it's okay. We can come back to it, but I have to say this is a vote where there were a lot of people abstained, so which might mean vote for the coffee break, for the early coffee break, but which I might also join, but but let's so, but first maybe an interesting thing to do is to go back for a second to the classical systems, right? Because in the classical systems, we have integrability, and we have Kolmogorov-Arnold-Moser theory, which tells you that there is some stability of quasi-periodic motion with respect to integrability breaking perturbations, right? Those estimates work for few body systems. Now here, of course, specialists can add or correct me. But in general, you expect quasi-periodic motion to sort of quickly give way to the chaotic motion. MBL is not like that, right? And I mean, if you think about the picture I described, it is really sort of closely related to KM. So it's you could say this is a quantum version of KM theory, right? One big difference, so this works as you take the number of degrees of freedom to infinity, right? And really you have this stable integrals of motion, right? And on some basic level, this is related to the discreteness of the spectrum in the quantum case, right? So, but that's one way of qualitatively looking at it as a quantum version of KM theory. Okay, so this is, of course, Emmanuel will cover in detail, but in general, so what people have been studying in experiments is, first of all, seeing how system either forgets or doesn't forget the initial, some initial configuration, like we talked about in the quantum quench. And if it does not forget, this is indication of MBL. And so that was, this is really the first experiment from Emmanuel's group in 2015, observing, a broad regime where system remains localized at the available observation times. And people have also, measured various proxies, for example, for entanglement entropy, seeing the signatures of this slow logarithmic growth of entanglement. Both of these are experiments with ultra-cold atoms. And now I think, well, this might bring us back to IMBRI, but still let us talk about a few open questions. And what is really sort of most difficult that we don't have a good handle on? Well, at the basic level, the way you describe this technically, you start from the infinite disorder limit and you start doing perturbation theory, right? Of course, disorder potential is probabilistic, so there are spots where it works out better than in the other spots. So in general, a strong disorder, it works out pretty well, right? So you have big chunks where perturbation theory worked out. You've constructed the eigenstate of that block. It has area law entanglement, all the nice things we discussed. But then there are rare instances where you find blocks of spins where disorder happened to be weak. And you cannot do perturbation theory. You have to do degenerate perturbation theory. Or maybe disorder happened to be so weak that this acts as a small thermalizing system. Of course, finding a big chunk like that is exponentially unlikely, right? Because it would require disorder potentials of L spins to align somehow. And I have to say, I'm not sure why I wrote obstacle for 2D. That comes from, but okay, just ignore this. I think this makes adds no value. And then the issue is that now you'll connect this region which happened to be thermalizing to the localized one, right? And you would say, well, but what does a thermal reservoir, even a small one, do? It can thermalize things, right? So then you have to somehow join them together, and maybe this spin, which used to be localized before I connected it, becomes entangled with the bath when I try to construct eigenstates. And then, so there we don't really have a good analytical control of how to describe this intermediate state, which is, clearly has slow dynamics, but not fully localized. That simply we don't have a good idea. And moreover, right, you can take this argument and say, well, if a spin is nearby, right, in general you would include it, and you would sort of, maybe you'll keep the bath growing. And so, Francois Houveniers and Wojciech de Rock really developed this argument and showed that in one dimension, this growth stops at some point, provided your localization length is short enough. But in 2 dimensions, if you take this argument at face value, then you would arrive at the conclusion that the bath grows faster than the, parametrically, so you always compare matrix element to, to the level spacing of the bath, right? And you would find that matrix element somehow at some point becomes larger than the level spacing. So you would expect that it would be a very, very slow but growing bath, right? Yeah.
I'm a bit confused by the expression a small bath.
Mm-hmm.
Kind of an oxymoron in statistical physics. So bath means larger than 1. You mean a system size that is much larger than 1?
Well, small bath meaning let's say it's a finite size, right? It's a chunk of, I don't know, 10, 20, 50 spins, right? Larger than 1.
Larger than the only one that they need to.
Well, so the argument does not.
The sort of bath is that the idea of a bath is that it's not influenced. It has its internal properties which are not influenced by the light.
Yes.
So if it's small, I don't see how it can happen.
Yeah, indeed. This is very much so. These arguments are very much, I think, actively discussed. So this is not a finished story, but still, you can imagine that you have a system, which has finite number of levels, right? But they're well entangled such that when you couple a spin to it, it would also get entangled, and your joint eigenstates would look like that, right? Right, with some coefficients. So
There seems to be like a passage from first line to the second, which I don't understand. Isn't your band just a part of the small potential, basically? Small deodorant?
originally, yes. But then you also, right? So the way you do this perturbation theory, so you make transformations which eliminate kinetic energy at short scales, but then you produce something smaller but on a bigger scale. So there would be something you would produce which couples this chunk to this one, right? And then the question is, what does it do? And again, these arguments are not rigorous, but at the same time, there are things that people thought about. I would say relatively long. Well, by the time scale of the field, maybe not that long, but some non-zero amount of time. And I would say nobody found a clear gap in them, but they have not been made more rigorous, and they have not produced a verifiable, let's say, verifiable estimate. Although there are some, simpler models which show that this physics appears with sort of coupling a small random matrix system to a chain of decoupled integrals of motion, something like that. So that's also the work that Francois and Wojciech plus I think one of the PhD students did, which is very, very nice work. Right, so here I would say the question is, what stops if you're in 2 dimensions, right? If this is not true, what stops the growth of the bath, right? Now, and another important question is, how big should be this inclusion? That's not in the literature. There is no statement that it has to be this many spins which are in resonance. And so maybe these things are so rare that you really don't care. And so in here, here also I'll show something that, I'm sure Emmanuel will talk a lot more about. So that's another experiment from the Munich group, now in 2 dimensions, right? And they found signatures of MBL in 2 dimensions. Of course, naturally there is some observation time you have, right, before external dissipation kicks in, but it's a pretty long time, right? And those things are hard to simulate classically in general because, tensor network methods are a lot more developed in 1 dimension, and that's why I would say, I don't know, 95 or 99% of what was done is in one dimension, really, including Imbri's proof. So in 2 dimensions, we have some numerics. So there has been an attempt of tensor networks simulation to construct integrals of motion, and they find something consistent with MBL in 2D. There is also time-dependent variational principle, gradually increasing the system size from quasi 1D, where they say no, they seem to extrapolate it to something delocalized. And then there is work from Fabien's group, where they study a 2D constrained model. Because it's constrained, you have a slower growth of the Hilbert space, and then there also they see nice signatures of MBL. Right, so you see that this is very much an open issue, right? Again, at the end of the day, maybe just putting a good bound on this rare region effect would be good enough, because ultimately what we care about is that the system does not thermalize while we are doing the experiment, and we are certainly in that realm. Yeah. Well, that depends. So this one constructs Leoms. This one checks more or less, similar to what is done in the experiment, whether initial pattern relaxes or not, right? I assume so. This Fabien, of course, will. I don't know. Do you want to comment? But in general, I mean, the challenge is that it's hard to simultaneously access large system and large time limit. So you either have one or the other. And I think here would be a good place to stop, actually, because I think I covered more or less all the basics of MBL, right? Except for Imbri, but that's maybe for another time. And there, I think it's a good moment to take questions. So there is a few more minutes for questions. Interactions? Well, yeah. Yes, okay. So the question is, do you need interactions in the Imbri's proof? A priori, no, but I think he would like to understand the interactions. So but the proof would work also without them. I think he also has a earlier paper without interactions, where, yeah, similar technique. Well, it opens. So the question is whether, when you're thinking about systems such as superconducting qubits, whether it's good to avoid ergodicity and avoid thermalization. I would say yes, because it opens new possibilities. And that's something I did not get to, but maybe I'll get to on Thursday, which are implications of what happens. Well, I guess we touched on that already, right? So there are integrals of motion that. Well, for quantum computing, you need lots of qubits and no decoherence. So here, I would say what I'm describing has not been directly, let's say, useful, right? Except, okay, I mean, people use some similar tricks. You want to detune frequencies of qubits as far away as possible from each other to avoid resonances, right? But I think this part of the story does not have a immediate application to quantum algorithms, today. Yeah.
Other questions or comments? Yes.
Is there a need that the interactions have to be of a specific kind? It's just that they're near neighbors, that's sufficient.
Sorry, say the last thing. Right, I did not get it, so maybe you can repeat it, and then I'll repeat what you said.
Interactions, is there a need that they have to be of a specific
So the question is, do the interactions have to be of a specific kind to see the entanglement? No, no. So as long as they're local, you would see this phenomenology. Now, one caveat. So if you have a system with a lot of symmetry, for example, if you have a SU2 symmetry, then things look different, right? So non-abelian symmetries are not good for this type of localization because they impose some constraints of what entanglement of eigenstates should be like. But there is still an interesting non-ergodic regime you find, but it just has different properties. But apart from that, there is no constraint on the form of short-range interactions. And maybe, I don't know, if there are no questions, well, if there are, please go ahead. I think they want the coffee, but yes, okay. Before they start.
This is perfectly on time.
Yes, and no, I just wanted to ask, what would you prefer I do for Thursday? Because I could do a few things. I could talk more about sort of continuing with MBL and talk about implications and MBL in periodically driven systems and a little bit, new dynamical phases of matter. I could also talk about other ways to break ergodicity, quantum many-body scars, and pre-thermalization. So would that be more interesting? So quantum scars and pre-thermalization, I think that I could do that. That's 45 minutes, right? Yes. Yeah. Okay, I think we can do that then. At least I saw some, yes. Yes. I could see that they would like it, so.